Hi everyone, welcome to the second lecture in our Chapter 17 Blood series. In this one, we are going to get into some of the parts of blood. We're beginning with plasma. This will be another relatively brief lecture, and then after this one, everything's going to be really picking up. So go ahead and get through this lecture and then be prepared for some pretty intensive lectures after this. So, as always, let's go ahead and begin with our not really attendance questions. First, what is the primary stimulus for ADH? And next, what is the ECM, extracellular matrix, of blood? Go ahead and pause the video, try to answer those. Hopefully everyone has done that, so let's see what the answers are. The primary stimulus for ADH, I had mentioned early on the first time that we talked about ADH that we would be talking about it all semester long, and that primary stimulus would be coming back over and over. So the primary stimulus for ADH is an increase in plasma osmolarity. And next, what is the extracellular matrix of blood? Well, remember, extracellular matrix in general is that area outside of and between cells, and in connective tissue, which blood is, it's really extensive. There's a lot of extracellular matrix, big spaces between the cells. So in blood, the extracellular matrix is plasma, which is the topic of today's lecture. So let's go ahead and start talking about plasma. What is it? What does it look like? What's its function? What's it made of? So plasma, which we see here, if you've ever donated plasma, you've seen this. It looks a lot like urine, and as I mentioned before, it's very similar to urine. And what we'll learn later in the semester, it is the foundation from which urine is made. So here we see plasma is about 55% of whole blood. Now that will increase and decrease based on things like hydration and number of red blood cells, things like that. But on average, remember the average healthy adult white male, average is about 55% of whole blood. And when we look at it, we can see that it's this kind of straw-colored or yellow, translucent, kind of thick material. Not really thick, not as thick as blood, but we can kind of get a feel from this picture that it's a little bit thick. So what is plasma made of? Well, like everything else in the body, it's mostly water. Water is about 90% of the volume of plasma. And so water is responsible for dissolving a lot of the stuff that's in blood. It's also responsible for absorbing heat. Remember the properties of water from Bio 137. But what's dissolved in that water to make plasma? Well, there's electrolytes. Electrolytes are the most abundant of the solutes if we just count number. Now, this isn't mass or anything like that, but electrolytes are by far the most abundant solutes by number. And what are electrolytes? Well, electrolytes are things that when you put them in water, they develop a charge. They become ions. So we have cations, the ones that we mentioned back in 137 regularly: sodium, potassium, calcium, magnesium, and anions, the ones with negative charges, which we didn't mention quite as much in 137, but will a lot in this course. We have chloride, which is Cl-. We have phosphate, sulfate, and bicarbonate. So all of these help maintain the osmotic pressure of plasma, and they also help regulate blood pH. Now, next we've got proteins, and there are dozens of different types of proteins in the plasma, but the ones that we are concerned with right now is albumin, globulins, and fibrinogen. And proteins in general in the blood make up about 8% of the plasma by weight. All of them contribute to the osmotic pressure, which we will talk about in just a little bit, but they all also have some other functions. So albumin. Albumin is the most abundant plasma protein. Most of the proteins in the plasma come from the liver. Not all of them, but most of them. Albumin is the primary contributor to the osmotic pressure of the plasma. And again, we'll talk about osmotic pressure in just a moment. If that's still a little fuzzy for you, just know that albumin, its primary function is to contribute to osmotic pressure of the plasma, and it contributes most to the osmotic pressure of the plasma. Next, the globulins. So there are different types of globulins. There's alpha globulins and beta globulins. These are transport proteins. They are also produced by the liver. Their job is to transport stuff that doesn't readily dissolve in the plasma. So remember we talked about some hormones like the steroid hormones. They need carrier proteins. Here we go. When we absorb fats and oils from our meal. Here we go. When we get our cholesterol checked and they talk about HDLs and LDLs. Here we go. These are all tied to the alpha and beta globulins, the carrier proteins. But gamma globulins, completely different. You've heard of antibodies, especially with COVID, close behind us now. When we talk about proteins and we talk about gamma globulins, that's what we're talking about. Gamma globulins are antibodies, and we will discuss exactly what antibodies are later in this same chapter. But gamma globulins, antibodies, they're the same thing, just two different names. Next, fibrinogen. Fibrinogen is a soluble protein that's found in the plasma. It just circulates in the plasma, also produced by the liver. And normally, fibrinogen is just, circulating, doing not a whole lot of anything. It's there, it's fibrous, but it's soluble. So you wouldn't really detect it easily. Now, when we start talking about blood clot later in this chapter, we're going to come back to fibrinogen and see how does it stop being soluble and help with blood clotting, because that is its primary function. All right, now we've moved away from proteins. What else do we see in the plasma? We have non-protein nitrogenous substances. So really that just means things that are based on nitrogen but are not protein. Well, even though they're not protein, most of them came from protein. So when our cells break proteins down through metabolism, well, it produces waste, and that waste will have nitrogen in it. Things like urea, uric acid, ammonium, creatinine, all of those things are metabolic byproduct waste, and they all have nitrogen in them. We also see nutrients in the plasma. So when we eat or drink and we absorb those nutrients, it gets into our blood and is dissolved in the plasma. Respiratory gases, oxygen coming from the lungs going towards our tissues, or carbon dioxide waste from our tissues going towards the lungs. Now, most of these respiratory gases will bind to hemoglobin, carried in the red blood cells, but some of them dissolve in the plasma. And lastly, we kind of already mentioned hormones. Some hormones, the amino acid based hormones, they're loose in the plasma. And then the other hormones, the steroid hormones and the thyroid hormone, those are bound to proteins in the plasma, like we mentioned earlier. So let's talk about concentration and viscosity and osmolarity. So concentration is really just how much of something is dissolved in something else. So if you put a little bit of salt in some water, we have a certain concentration. If you put more salt in the water, well, now it's more concentrated. Or if you boil that water and some of the water leaves as steam, well, the salt stays behind. So again, it's more concentrated. So concentration is really just the comparison of how much water or other liquid compared to the amount of stuff that's dissolved in it. But we can kind of also bring in viscosity and osmolarity, which are related, and sometimes we use them a little bit interchangeably, but they're not the same thing. So first, let's talk about viscosity. Viscosity, by definition, is the resistance to flow. How easily does a liquid flow? The more viscous it is, the less it will flow. And we can also kind of think of it as the thickness of a fluid or the stickiness of a fluid. A common example is mineral oil versus water. But a better way to think of it, and it's not exactly the same thing, but imagine pouring water through a garden hose and pouring ketchup through a garden hose. Which one of them is going to flow easier? Well, water will flow easier. Ketchup, or mineral oil, has more viscosity. It's going to resist flowing as easily. Blood, whole blood, is about 4.5 to 5 times more viscous than water, and that's primarily because of the red blood cells. Blood would not flow through a garden hose as easy as water would. Now, if we just take the liquid part of blood, so just the plasma, remember plasma with those things that we just talked about dissolved in it, plasma is about 2 times as viscous as water. So both of them would flow through the garden hose pretty easily, but water would flow easier because plasma is 2 times more viscous. And that reason is because of those proteins that are dissolved in the plasma. So when we get to our next unit or block, we will be talking about blood flow. How easily does blood move through the blood vessels? And that comes from viscosity. The more viscous the blood, the harder it is for it to move through the blood vessels. That's going to be a really important concept, because when we start talking about cardiovascular system, well, then included in that, we're going to start to talk about blood pressure and cardiac output and stroke volume. All of those topics are going to be aimed at moving blood through the blood vessels. The goal is to get blood with its nutrients and oxygen to the tissues and to get waste products away from the tissues. So blood needs to be able to flow relatively easily. The more viscous the blood is, the harder that flow will be because of the resistance to blood flow as viscosity increases. Now, similar, osmolarity. Osmolarity we talked about back in Bio 137, especially when we were talking about diffusion and osmosis. So osmolarity is the molarity of dissolved particles that cannot pass through the walls of the vessel. So we have a couple of words here. One that I want to talk about is molarity. Molarity is a common chemistry concept. It is a measurement. We can kind of think of it as the number of dissolved particles that can't pass through vessel walls. Well, when we start talking about blood vessels and the different types, we're going to get to very, very small blood vessels called capillaries. And at the capillaries, that's where things that are in the blood move out into the tissues, and things that are out in the tissues move into the blood. That's where exchange takes place. Those nutrients, that oxygen that blood is carrying, it needs to be able to pass through the vessel walls at the capillaries. The waste that builds up in the tissue and the carbon dioxide that builds up in the tissue needs to be able to pass through the vessel walls to get into the blood to be carried away. But there are things in the blood that do not leave because they are either too big or they have too much charge of a certain type. Whatever the reason, they remain in the blood and cannot pass through the vessel walls. The more of those things there are, the greater the osmolarity. So let's think of this another way, especially those of you that had me before for Bio 137. We said solutes suck. Solutes pull water towards themselves. All right, let's build on that. If the solutes are too big to fit through the vessel walls, or if the solutes have the wrong charge to fit through the vessel walls easily, solutes are going to remain in the blood vessels. And what's that going to do? It's going to increase the osmolarity. So if we increase the osmolarity, it's going to resist water passing through the vessel walls also. Instead, it's going to pull water into the vessels. So osmolarity is going to contribute to something called colloid osmotic pressure. Putting everything that I just said together, the more solutes that remain in the blood vessel because of whatever reason they cannot pass through the vessel walls, the greater the osmolarity. The greater the osmolarity of the blood, the greater the colloid osmotic pressure. Less water and nutrients will leave the blood at the capillaries, and instead more water will be pushed into the blood at the capillaries. The greater the colloid osmotic pressure, the less will leave the blood, the more that will enter the blood. And that is because of the molarity of dissolved particles that cannot pass through the vessel walls. That is because of osmolarity. This determines filtration and reabsorption. So really that's what I just said. Filtration, that's substances leaving the blood. Reabsorption is substances moving back into the blood. That's based on colloid osmotic pressure. Colloid osmotic pressure is based on the particles that cannot pass through the walls of the vessel. So osmolarity and viscosity, they are related, they are not the exact same, and also both are related to concentration. All right, again, short lecture today, so that's all that we will talk about. That's where we will stop, but this was a pretty intense lecture there at the end. Make sure to listen to that a few times. Make sure to wrap your head around it. If you do not understand it, ask questions, study, because now we are into the weeds where everything we talk about is going to be built on throughout the semester. Osmolarity, viscosity doesn't go away. Make sure to ask those questions. All right, take care. Hopefully I will hear from you, and I'll talk to you next time.